Thank you, Suram. I'd like to thank the organizers, too, for organizing this workshop. I got a lot out of it. And some of what I've learned is actually reflected in the talk, in the slides. That's one of the advantages of being the anchor speakers. You can sort of adaptively change your talk as the week wears on. So, joint work with Yuguang Gao, who's a PhD student at Cornell that I'm working with. And, okay, we're going to look at channel coding. So it's a bit different from some of the prior talks, but there's a significant learning component to what we're looking at. Specifically, like how much learning do you have to do in order to communicate at capacity over a channel, okay? So that's the question. Maybe I should declare at the outset that we don't really have like a completely conclusive answer to this question. I'll declare that now. It's helpful if your expectations are kind of low as we move on. So keep that in mind. Okay, so let's start with the basics. I wasn't sure how fast to go through this, so I'll go kind of fast, and you can please stop me if you have questions about this. Is the kind of the basic Shannon theory communication setup. So when I say channel in this talk, I mean throughout what we call a discrete memoryless channel. This is basically a stochastic matrix, like from one alphabet X to one alphabet Y, and we think of this as like a model of a channel. So at each time you can input a symbol from X, and the output is random, and the distribution is the row of the matrix corresponding to the input X. Okay. And you use this channel many times, so we want to communicate over it. So we have an encoder that would take a string of n bits. It would map it to a string of n x symbols. This channel would produce a random string of outputs according to this matrix. And given x, the string is independent over time. That's the memoryless part. And then you design a decoder that takes the y string and then tries to recover the bits. Okay, so that's the setup. And the classic theorem in this business is that for such a channel, you can define a capacity, which is the largest rate r for which this error probability, the end-to-end error probability, will go to 0 as n goes to infinity. And for most interesting channels, this thing's positive, and you can kind of compute it explicitly as the maximum mutual information through the stochastic matrix. Okay. So this is very classical stuff. It's also known classically that if you allow perfect feedback to the encoder, so it sort of sees the outputs of the channel kind of causally as they come out and adapts, that you can't achieve higher rates. And throughout the talk, we're going to assume we have this feedback link here. That's kind of important. Okay, so we'll assume, I mean, obviously, real feedback is sort of not ideal like this, but this is the model. We'll have ideal feedback like this. Okay, so that's for a known channel. Right, known channel. In real life, you don't know the channel going in. You've got to somehow learn it, adapt to it, make do with some uncertainty. So what can we say about unknown channels? And one of the things I've learned from this week-long workshop is that I should view everything as a minimax problem. So here is channel coding as a minimax problem. Okay, so fix the input alphabet, fix the output alphabet, fix the rate, some fudge factor, some back off epsilon. Okay, then you can strengthen the previous theorem as follows. So you can find one code for each block length, whose rate is at least r minus your back off. Okay, so that the error probability of that code over any channel, when you maximize over all channels between these alphabets whose capacity is at least r, so it can kind of support the rate that you're targeting. Okay, this quantity here will tend to 0 as n goes to infinity. Okay, so you can sort of drive the error probability to 0 uniformly over all channels connecting these two alphabets, as long as the Shannon capacity in the sense of the previous slide exceeds the rate that you're targeting, minus, of course, there's some little gap there, right? Okay, so I mean, this is you can find this proven in the literature. The first reference I could find is actually quite recent. I think the result was kind of known, kind of as a folk theorem prior to that. And the proof is very simple. I mean, you just sort of allocate some vanishing fraction of your block to training. So you just sort of probe each input, see what happens, estimate the channel, and then proceed as though your estimate was exactly right, and just use that for the rest of the block. Okay, so that's the scheme that proves this result. Okay, so sorry. Yes, this is absolutely with feedback. The feedback is really important here. Otherwise, you can't learn the input distribution. Yeah, so you need the feedback. Yeah, and there are subtleties here about whether you allow randomized encoders or not. When there's just one channel, it's easy to de-randomize. When you have multiple, not so simple. But anyway, okay. So yeah.
In this theorem, fn g no w.
No. That'd be the Maximin, right? That'd be sup inf. Yeah. They're unknown. Yeah, that's the crucial statement here. So you can find one code for each block length that kind of handles all the channels in this set. Okay, so this theorem is like such an established part of the canon of the field that I feel entitled to bash it a little bit. Okay, so one thing I don't like about this theorem is that it really relies, the proof here relies very crucially on the fact that learning the channel is absolutely free. Okay, you pay asymptotically, you pay no cost for learning the channel. Okay, so it's like there's no penalty for not knowing it, right? This is not realistic, in my view, right?
Is that you are restricted to channels of certain capacity.
Yeah, but I mean, if the capacity was kind of below the rate I wanted, even if I knew it, I couldn't work with it, right? So in some sense, it seems like no penalty at all for not knowing it. Okay, and moreover, you don't have to be very smart about how you learn the channel, right? In this scheme here, I mean, these are very naive schemes to learn the channel. It's fine. You can be very, very kind of lazy or coarse in your learning of the channel. And this is not realistic, right? In real life, you don't know the channel, you got to learn it, and the learning process is important. It has a non-trivial cost. You want to minimize it. People work very hard to try to dream up ways of kind of minimizing the cost of training and learning the channel at the beginning, and that's just completely lost in this result. Okay, so the question is, how do we modify the model to kind of capture that cost? Okay, and there are a few ways of doing it. You could just, for fixed parameters here, you could study the speed of convergence in N and compare that to the sub-inf statement, and then study schemes that do that. And I know there's Chomperton, Teletar work on essentially that problem. I think is very good. So the approach that we're taking is a little bit different and maybe more in the theme of this workshop, which is we're going to study the speed of convergence here as a function of the alphabet sizes. Okay, so here the alphabet's fixed completely. You could ask, how, as I start varying the size of these alphabets, how does the speed of this limit change? You sort of expect it to slow down as the alphabets increase, right? You're taking the supreme over a bigger set. In terms of the proof, it takes longer to learn the channel, the larger these alphabets are. So you'd expect it to slow down, and can you kind of quantify that slowdown? And then maybe quantifying that will kind of force you to come up with clever training schemes. So that's the program here.
So this whole theorem is for finite x and y.
It's for finite fixed x and y, yes, finite. All the alphabets in here are finite. It's another global assumption. Yes, David?
It's like an odd formulation, right? Because sometimes the x could be a discretization of a continuous space.
Okay, interrupt you for a second. So you mean this theorem right here, you think is an odd formulation, or what might change?
The very last question, how large must n be?
Yeah.
So I'm thinking maybe often that x is a discrete alphabet, but it's a quantization of an underlying continuous alphabet. Mm-hmm. So you increase n, somehow the problem should not become more difficult.
True, yeah. So in a sense, you're saying, I mean, the real challenges we care about are sort of intrinsically continuous, so why would we use these discrete models? Yeah, so you could certainly formulate it differently with these sort of continuous forms. I mean, we're sort of following the traditional information theory approach of starting with DMCs and figuring that out first, and then looking at how it extends to continuous channels. But I mean, you're right. I mean, in a sense, the DMCs that we're going to be studying, they're going to come up, they'll kind of achieve the supremum, are not really going to have a lot of structure across the rows where you expect to have that structure if this is like a quantized version of a continuous channel. So you're right. Yeah.
I mean, a different way of formulating this is, what's the dependence on like the Lipschitz constant of your continuous thing? Yeah. I mean, like the alphabet size is, for any reasonable discretization.
Yeah, that would be a different formulation though, right?
Yeah. No, but it's essentially the same, right? Like, if you have a rather non-Lipschitz function, then when you discretize, presumably you're going to pick more chunks. Anyway.
So I mean, maybe here's an answer like better than my previous one. May not be better than Greg's, but better than mine is. In those sort of channels, you could just sort of ask like, how fast is the convergence here as a function of how many parameters are in the channel law, right? So you don't know the channel law. It's in some family, it's parameterized by some family. There's a certain number of parameters you don't know that you sort of need to learn if you want to use this approach. And what is the speed of this convergence as a function of how many parameters there are in that? So we're starting with this model as sort of a simple model here. The number of parameters is like the product size. Okay, but you consider other richer, more complicated channel models that parameterize it differently. Yeah.
So when you say how large n should be, I'm not sure that I understand.
Okay, so this is intended to be in.
Probability of error is a function of, let's say, right, n, x, and y, right?
Yeah.
So if I give this as a function, like you wanted to bound it by f.
Okay, so this is not intended to be like, this is intended to be like a very informal lead-in to this one right here. Okay, all right. Okay, so yeah, I mean, ultimately, you'd like to, ideally, sort of for a fixed n, for fixed alphabet size here, rate r, you'd sort of characterize like this inf sup, right? Okay, but we'd like to, that's hard to do. We're going to back off and characterize something relatively coarse, actually, which is just for what alphabet speeds is the limit 0 and for which is it not. Okay, So we'll say a pair of alphabets, X and Y, support universal communication if for every backoff, for every rate, then the limit continues to be 0. Even now when you're taking supremum not over alphabets from a fixed alphabet, but over xn, when you use block length n, when your code is block length n, supremum is taken over the alphabets xn and yn. Okay, so these alphabets are potentially growing with n. Okay, so as your block length increases, you have sort of more time to communicate, but you have more to learn if you're using a learning-based scheme. So it's not entirely clear how this would play out. Certainly if the alphabets are fixed, and if you just choose all of these to be the same with n, this reduces to sort of the previous result.
Actually, even then, it's more general than the previous result, because R is allowed to change with n.
No changes.
Okay, that's true. Yeah, good point. Okay, that's not a big advance, but yeah, you're right. That's very true. And since R varies, we allow multiplicative backoff in addition to, you've got to ensure you have a multiplicative backoff and an additive backoff when R is growing. Okay, so the question is how fast can the alphabets grow with n so that this is still true? If the alphabets grow really fast, then you might expect that the convergence is going to slow down so much that it just doesn't converge anymore to 0. All right. So there's certainly connections to the sort of lossless compression version of this story studied by various people who are here, Alain and Stefan. We heard about this earlier this week, and Wojtek and Marcello and so on. This problem, I think, is a bit more complicated. For starters, we have 2 alphabets rather than 1, right? I mean, in source coding, you have just the source alphabet. Here you have X and Y, and it's not clear a priori how interchangeable these alphabets are, right? Like a big X and a small y versus a big Y and a small x. It's not clear which is harder. Okay. So what can you do? So, okay, so having formulated rather coarsely, I'm now going to coarsen it even more. So let's just look at powers. So assume that the input alphabet goes to the end of the alpha, output is end of the beta, and we'll study for what alpha and beta does this limit equal 0. Okay, so I agree, this is a very coarse formulation, but this is what we can talk about. Okay, so let's start with the training scheme. The scheme that just learns the channel first and then communicates based on what is learned. So the sort of classical proofs that work for a fixed alphabet kind of break down quickly when the alphabet starts growing. But if you just keep the scheme the same, at least keep the same kind of philosophical scheme and just sort of push the analysis, or do the analysis kind of more refined or more delicately, then you can show that as long as the product size grows sublinearly, then you're okay. And this is maybe not unexpected because that's the total number of parameters in your distribution in some sense, right? So if it takes like n tries roughly to learn a distribution from an alphabet of size n, here this is like the number of unknown parameters in your matrix. So that's kind of roughly what you're trying to learn. Was there a question? Okay.
You mean for every alphabet plus beta less than 0?
Sorry.
For every, right? Not for some.
I'm sorry. Yeah. So yeah, I should just say there should be no for just if that's true. I'm sorry. Yeah. I changed the slide at the last minute, and I think I botched it up. Yeah.
Is this if and only if?
No. This is one particular scheme. Works if this condition holds right here. So we'll get to the only if right now, actually. So, okay, so for what comes later, it's helpful to plot this. Okay, so here's alpha, here's beta. So the scheme handles this regime right here. And there's the question, is this optimal? It's
straightforward, like first training, and then...
Yeah. So the only non-trivial thing is kind of analyzing how fast the alphabetic growth rate it can handle. Okay. So this is certainly optimal if you insist on learning the channel. So you can study a separate problem where you just forget communication and just ask, like, given the alphabet growth rates, can you learn the channel or not by the end of the block length? Okay. And that you can show, at least under this setup, is exactly this region here. Okay, it's maybe not surprising. Outside, the only thing that's kind of subtle in establishing that is that you don't constrain how many times the encoder uses each input. You just constrain the total amount of time. And it can allocate time among the inputs however it wants. So the time it spends on one, really? Okay, so the time it spends on one input, could sample path dependent, right? So it's a bit subtle there. So anyway, so then the question is, if you want to establish is this optimal, the question is, establishing whether it's optimal or not is sort of tantamount to determining whether you have to learn the channel in order to communicate at capacity, right? And when we began this, I was very hopeful that you would not need to learn the channel, because if you look at the training-based scheme, first of all, the encoder does not need to know the whole matrix. It only needs to know the capacity-achieving input distribution, which is a much lower dimensional object. So it's not clear you have to learn the whole W to figure out this argmin. And then the decoder doesn't use the train at all, actually, in the proof. Okay, so we had some hope that you'd be able to come up with more clever schemes that kind of end out here. But we have 3 impossibility results that say in various directions you try to move, that you can't do it. And so I'll show you them sort of increasing difficulty. So first of all, if the input grows superlinearly, this is not going to work. So this region's out. And that's kind of obvious. I mean, it requires a proof, but essentially if the input grows, I guess we have linear or superlinear. If it grows superlinearly, you can't even touch all the inputs once over the course of the block. So there's no way you can communicate at capacity. Right? You got to at least test each input once and see what happens. So that's pretty clear. Okay. The other flip side, where the output grows linearly or superlinearly, is a little bit more interesting. And so let me say a few words about that. So for this, we sort of took the Minimax lower bounding techniques from statistics and sort of channeled them, so to speak. I mean, our risk function, if you want to call it that, is kind of complicated. So this is not a direct application, but you can sort of apply some similar ideas. So consider this channel. So 2 inputs. Let me stand here. So 2 inputs, like 0 and 1. And you have end of the beta outputs. And if you send 0, it's uniform over this set. Send 1, uniform over that set, right? Okay, so the capacity is clearly 1 bit. This is essentially like an identity matrix. You can coalesce these symbols. It's achieved by uniform input. All right, now let's let Wn be the set of all channels obtained via column permutations of this. They all have the same capacity, clearly. All right, and then consider the block mixture channel, like this. Okay, so given the input, you pick a channel out of this class uniformly at random, and then you apply that n times, generate the output. All right, it's not too hard to show that if these alphabets supported universal communication, okay, then you'd be able to find a code that operated at rate log 2 and over this channel with a vanishing error probability. Roughly, you can achieve log 2 over each channel in the class, and the error probability of the mixture is the mixture of the error probabilities. So if the error probability is low for each channel in the class, it's got to be low for the mixture. Okay, but you can show the capacity of this mixture channel has got to be quite a bit lower. Okay, and the argument there is as follows. So consider mutual information over the channels is the message, is the output, 2 entropies. This might be the first entropy decomposition we've seen all week. Right? It had to happen eventually. So here we are. Okay, you can never run the entropy of the output through a uniform distribution. Look at this term here is really the critical one. Okay, so think about the different terms in this sum. Start with just the first one, entropy of y1 given m. What's the distribution of y1 given m? Right, well, it was like the first input you're sending, right? So when you send the first input, you know nothing about the channel. All column permutations are equally likely. So all the outputs are equally likely at that stage, right? No output's more likely than another. So the entropy of y1 given m is log n to the beta. That cancels one of these n to the betas. Likewise, next step, distribution of y2 given this stuff. I mean, it depends on whether you send the same input twice or 2 different inputs. Suppose you send the same input twice. Okay, then the distribution of y2 given that information will look like as follows. So one of the inputs will have been revealed by the previous time step. But because the column permutations are all equally likely, then all the rest of them are the same. So this is essentially a uniform distribution over size alphabet size n to the beta. So that it's again like log n to the beta and cancels one of these. Okay, and the point is, I mean, you can keep doing this, and as long as you're looking at an index that's much lower than the output alphabet size, then the distribution of yi given the message in the past will be roughly uniform. And so you'll get log n to the beta, and in that regime you end up actually with a capacity of like 0 for this mixture channel. Okay, so that's not going to work. Okay, so no code can achieve capacity for all channels in this class, and I think what's interesting about this is that the optimum input distribution is no mystery here. It's uniform for every channel in the class. So it's not a matter of learning the optimum input distribution. It's more that the decoder can't really make sense of the output without a lot of training. That's really what's going on. Okay, so that's that. How am I doing? 7? Oh, okay. All right, so here's the, I'll slow down then. So here's the last of the 3 results. So let me just show you the picture, actually. So this is what we had before. So this is result number 3. So essentially what happens is we can show, if you can show any point is infeasible, then everything that dominates it is also infeasible, right? So essentially what we show is that like everything on this line here is infeasible. This is the kind of points where alpha plus beta equals 1 and where the output alphabet is bigger than the input alphabet. Okay. So I'll just say a few words about this. Let me kind of just explain the square point, the square root n, and these ones are kind of similar. And I'll maybe say a few words about that if I can. Okay, so suppose the matrix, the stochastic matrix that's unknown is square. And let me again generate a class that's sort of hard to communicate over. And I'll generate the class as follows. Put half on the diagonal. Okay, so that's just there deterministically. And then I'll pick some number gamma less than half, less than the power here. And then we'll randomly pick end of the gamma entries in each row. I'll just paint them with a blue square like this. Okay, and you put probability, put the remaining probability uniformly over those squares. Okay, so you do that for each row, and you get a stochastic matrix like that. Okay, and that's a randomly generated matrix in the class. All right, so you can work out the capacity of a typical realization of a channel in this class. That's kind of standard stuff. Let me point out the row entropy is deterministic, right? The entropy of each row is the same. Doesn't really matter where you put the blue boxes. So the capacity is random only to the extent that the entropy of the output kind of depends on what input distribution you use and so on. But it's roughly a uniform input will give you a uniform output. So you can work out kind of what the nominal capacity is for each channel in the class. And it's essentially achieved by a uniform input. Okay, so then the point is if you take the block mixture version of all the channels in this class, you can again show that if you could achieve capacity for every channel in the class, you would achieve the same capacity, the same rate on the mixture channel. And by similar reasoning to the previous result, you can show you can't do that, essentially because the decoder has to learn the positions of all these things in order to make sense of the output. All right. And what's interesting about this case is, in the previous case, it couldn't really do it for either. There are only two rows, right? In the previous case, the decoder couldn't learn either row. It didn't have enough time. Here, it's only square root of n across, right? So the code could learn some rows very well if it wanted it to. I guess it could learn like up to square root of n rows, roughly. So it can learn some rows really well, but it can't learn all of them. And that's kind of the key thing here. And that's actually why we have these halves on the diagonal. So when we first started, we didn't have the halves. We just did the blue thing, thinking that would be enough, trying to mimic the previous result. And it didn't work. And the reason it didn't work is that if you just have the blue things, it's possible for the code to kind of, the encoder, think of it, just kind of start trying rows and learning rows, and eventually it can find a subset of rows that over which a uniform input gives you a uniform output. And once it has that, it doesn't need the rest of the rows at that point. It can just use that smaller set of rows to achieve capacity. So it doesn't have to learn everything. And that sort of defeats the purpose of the converse proof, right? So one of Yu Guang's many contributions to this was to come up with the idea of putting the halves on the diagonal. And when you do that, you sort of force the encoder to use all the inputs. Like there's no hope of achieving capacity if you don't use all the inputs. And if you use all the inputs, then you've got to learn them kind of by the reasoning of the previous result. And so that's it. Okay, so that's kind of where we stand. Just for comparison purposes, so it was asked, what happens if you do the reverse? So suppose you can form it the same way as before. Suppose you just swap the sup and the inf. Okay, so now the code can depend on the channel, but you still require the convergence of the error probability to be uniform over all channels in the class. Okay, so for this we can give a much more conclusive answer. It was very different. Okay, so you can show that the alphabets will allow this, okay, if their growth rate satisfies this condition. Okay, so there's a couple of striking things about this. So first of all, the product alphabet size doesn't matter anymore. It's the minimum. It's not even the maximum, actually. It's the minimum of the two alphabets. Okay, and they can grow really fast. So in some sense, as long as either one alphabet or the either grows as like e to the square root of n or slower than e to the square root of n, then you're okay.
It's actually surprising that you need to restrict the alphabets at all.
Well, I mean, the capacity theorem is sort of based on concentration results, right? And if the alphabets grow really fast, then you can.
I think that this might hold even for continuous alphabets.
Well, I mean, we have some condition here. Yeah, we have some condition. Yeah. All right. Anyway, I mean, the upshot takeaway from this is that the knowing the channel buys you a lot. I mean, you go from kind of like linear growth rate of the alphabets in n to like e to the square root of n for one of the alphabets. So it's a big jump. So certainly the model is capturing like the cost of learning the channel in some sense. So it's a success in that regard. So must one learn the channel? So, and we don't know is the short answer, but I mean, it appears so in the sense that, all of this is blocked out. We don't know what's happening here. The reason this is harder than over here is that So when the input alphabet size is smaller than the output alphabet size, sorry, this is the other way around. When the input is bigger than the output, then even when the channel is known, you can show that there always exists a subset of inputs that's no larger than the number of outputs, so that the code can just use those inputs. So the code, when it knows the channel, it doesn't need to use all the inputs. It can use a subset of them. And so naturally, it's kind of harder to force the encoder to have to learn everything. You, in a sense, have to kind of construct a channel with good rows and bad rows, and the good rows are very few, and they're in unknown locations, and it's sort of hard to tell a good row from a bad row without learning the whole row. But at the same time, you can't allow you don't want the encoder to allow the encoder to communicate using bad rows. Like it has to use the good rows, it has to find them. So that's sort of what needs to be done to fill that in. And there are certainly connections to like the impossibility results for learning the entropy, because in some sense, like how good a row is kind of tied up with its row entropy, if you think about the mutual information decomposition, right? But it's more complicated than that because the output distribution matters as well. Okay, so I mean, even if this turns out to be yellow or whatever color this is, so that it's that all seems negative, then I mean certainly we're ignoring the subpolynomial factors. So there's some hope. And I guess here we showed if you have exactly linear growth, you can't do it. And exactly linear growth, can't do it. It's conceivable that maybe something in the middle here would allow linear growth. And then it's related to David's question at the beginning. So I mean, this is. It's certainly a very pessimistic channel model, and it's also a little bit weird, admittedly, in that we fix the alphabet, we fix the capacity, and the channel could be anything in that class. So it's a very big class, as we've seen. There are a lot of weird channels in that class. So even if these results are pessimistic, perhaps if you sort of restrict the class of channels to some smaller, more structured class, similar to what Stefan was talking about in his source coding talk on Wednesday, I think it was. Perhaps then you wouldn't need block lengths that are quite so large as a function of the alphabet size.
And perhaps the role of the size of the alphabet would play by the parametric dimension of the...
Could be, yes, could be. Although perhaps some classes, though, would be such that you don't necessarily need to learn all the parameters. I mean, here you do in some sense. You got to learn all the unknown parameters to communicate, but perhaps with other classes you wouldn't have to do that. That's all. Thank you.
I have one question.
Yeah.
So here you're considering the polynomial scaling n to the alpha and to the beta, right? Is it hiding some log factor, for example, which we saw in the entropy case?
I hope so. Yeah, I mean, we don't know. I mean, so in a sense, what's happening kind of right at the boundary in some sense. Yeah,
So for
we don't know.
alpha equals beta, and then you're at that boundary.
Yeah. So let me say this. So what we showed is if alpha plus beta is strictly bigger than 1, okay, then you can't do it. So that's the way here. Here we showed if alpha equals 1, can't do it. So there's no logarithmic factor hiding there. I mean, no logarithmic factor to our benefit, that, right? And likewise here. So, but it's possible in the middle, maybe something weird happens.
Yeah, so you seem to be pretty pessimistic about the missing thing. But is there any hope of there being a bit of magic? I mean, it's conceivable that you could that you can kind of just, all you want to do is find a couple of these good rows.
Yeah.
And there are lots of them, they exist. Sorry, to make a question. Can you articulate why you're so pessimistic about the...
Well, I think some of it's just psychological. I mean, I started thinking, and then more and more kind of got blocked off. I guess it's, if this point here wasn't, here, if we have linear growth in the input alphabet, then you can't do it, which is kind of obvious, right? So now I guess it's conceivable that you move just slightly in and then suddenly good things happen. But I don't know, it seems a little bit surprising. Yeah, no? So maybe do you want to be... I'm going to take over the session chair's job and just call people.
Maybe we will arrange the chairs for it.
Yeah.
Okay.
In the second case, where you have the channel is known, where you're looking for...
Oh, the second, yeah, okay.
Where you're looking for kind of that the probability of error should go uniformly to 0, right?
Yeah.
Here, suppose I told you that you're going to distribute channels, that if you knew them, I guess you're saying the reason this happens is they're channels that have very large alphabets, that they can just have the probability of error go very slowly to 0.
Yeah.
There's nothing you can do about it.
Right, essentially, yeah.
And once it's this big, then you can find such channels. That's
And once it's what?
once it's this big, once it's like bigger than this, then
Yeah, you can find such channels, yeah.
so that's the.
Yeah.
It's nothing to do with learning, right?
So there's no learning here, that's right.
Algorithm learning.
Exactly, but I mean, it sort of sets the baseline. Like if learning was not an issue, then how well could you do? So it shows that that learning is in a sense costing you a lot in the previous result. If there was no learning, then it jumps up to this. Yeah.
Time varying channels? Have you looked at that?
No, this is.
I mean, naturally, that's what you would be interested in. You have a fading channel.
Yeah.
Because otherwise, if it stays the same amount of channels, then you use.
Right. Yeah. But I mean, in a sense, so I mean, one way of trying to model that would be to say like you can't use the channel very many times before it changes. So kind of look at one block at a time now, and you're in, if you want to call it the learning limited regime, we don't have enough samples to really learn effectively, and how well can you do? And this asymptote is in some sense trying to capture that. I mean, if I'm looking, okay, I lost my plot, but if I'm looking in the, in here, then, I mean, this is sort of like capturing the learning limited regime. It's in the asymptotic sense, okay, but it's qualitatively, it's trying to capture the same notion. Yeah.
Look at this picture, right? Suppose that the encoder doesn't know the channel.
Yeah.
But the decoder does.
Okay.
Right? How does this picture change?
Good question. I don't know.
Some of your all your negative results where the input distribution is known, like presumably the decoder would be able to.
Well, here it hinges on the encoder not knowing what to do. So the way you prove this is you have a.
This one, yeah. What about
Yeah, up there, yeah. If the decoder knew, then our proof would totally break down. So it's very possible that would change things. And we looked at a source coding version of that, lossless compression, and looked at the situation where neither the encoder nor the decoder know the source exactly, and the one where both know it exactly, and one where the decoder knows it exactly. And in the case where the decoder knows it exactly, it's sort of in some sense equivalent to when they both know.
Okay.
So for lossless compression, at least, just putting the information that the decoder is sort of enough. The encoder can just kind of randomly bin, and then the decoder can sort of figure out from what it knows, and that's fine. So it's really there. It makes a big difference. Here, yeah, I don't know.
Let's thank Karen, I think.